to section 4.5, summary of curve sketching. So in this section, we're going to walk through the 8 steps that are involved in sketching the graph of a curve of a function. And we're going to be putting together techniques that we've learned in previous algebra courses, as well as our new calculus techniques, where we can obtain information about functions, their behavior, so that we can sketch a very accurate graph. All right, so the example that we're going to begin with is a nice polynomial, y equals x to the 4th plus 4x cubed. And as I work through the example, I'll also elaborate a little bit about what each of the steps are in putting together a sketch of these curves. So the first one is the domain. You want to identify the domain of your function. In this case, we have a polynomial. So the domain is all real numbers. We have no restrictions to worry about. Next step is you want to identify the intercepts, x-intercepts and y-intercepts. So to begin with, for the x-intercepts, we set the function equal to 0. So I'm going to set x to the 4th plus 4x cubed equal to 0. I can factor out an x cubed, and then I have x plus 4 is my remaining factor. This means either x is equal to 0 or x is equal to -4. Now remember, when writing intercepts, you always want to write them as ordered pairs. So my intercepts are 0, 0, and -4, 0. All right, that covers the x-intercepts. Now what about the y-intercepts? So to find y-intercepts, I substitute in 0 for x. So that would mean y equals 0 to the 4th plus 4 times 0 cubed, which is 0. And we already have that 0, 0. Anytime you have 0, 0 as an x-intercept, it's also going to be a y-intercept and vice versa. All right, next thing you want to check for is symmetry. And you do this by figuring out if the function is even, odd, or neither. Now, if a function is even, that means that it's symmetric with respect to the y-axis. Think of a parabola. That's your classic example. How do you check if a function is even? Well, you apply the definition. So you evaluate f of -x, and if after simplifying you end up with f of x, the original function, then that means it's even. Now, if a function is odd, that means it's symmetric with respect to the origin. Think of x cubed. That's a classic example. Now, how do you test if something's odd, if a function is odd? Well, same thing. The test is the same. You evaluate f of -x, and if you end up with -f of x, or the opposite of your original function, then that means it's odd. And symmetry can be a big help, especially when you're sketching a graph, because easily you can reflect and use some of the points that you've already found in other quadrants and save you some time. So let's see here, our function, remember, we had y equals x to the 4th plus 4x cubed. Well, I can replace y with f of x, right? This is a function. And now I'm going to test if we have any kind of symmetry. So I'm going to evaluate f of -x. That's going to be -x to the 4th plus 4 times -x cubed. Well, I get positive x to the 4th minus 4x cubed. Well, is f of -x equal to f of x? Is this the same as the original function? No. So that means it's not even. And is f of -x equal to the opposite of my original function? The opposite of my original function would mean I'd multiply all of the terms by -1. Well, -4x cubed, yeah, that changed signs, but x to the 4th didn't change signs. So no, this is not odd either, which means we have no symmetry. That's okay, no problem. All right, next thing we need to check are asymptotes. All right, so 3 different things to consider. First are horizontal asymptotes. Now, you have methods from pre-calculus for how to find horizontal asymptotes, and those are a great way that you can check that you did this next step correctly. But now that we're in calculus, when we're finding horizontal asymptotes, remember the horizontal asymptote tells you about the end behavior of a function. or a graph. So the end behavior is also found by taking the limit as x approaches positive infinity and negative infinity. And that's exactly what we're going to do right now. So remember, our function here, f of x, is equal to x to the fourth plus 4x cubed. So I'm going to take two limits. I need to know the limit in the positive direction as well as the limit in the negative direction. So the limit as x approaches positive infinity of x to the fourth plus 4x cubed. Well, let's see here. As x approaches infinity, x to the fourth is approaching infinity. So is 4x cubed. So this is just going to be infinity plus infinity, which is infinity. Now what about the other direction? So if I have the limit as x approaches negative infinity of x to the fourth plus 4x cubed, well, x to the fourth, that will still approach positive infinity. But 4x cubed, as x approaches negative infinity, will approach negative infinity since it has an odd exponent. So right now I have an indeterminate form because I have infinity minus infinity. One way to work around this is by factoring out an x to the fourth. So I have the limit as x approaches negative infinity of x to the fourth. I'm going to be left with 1 plus 4 over x. Now, why did I do that? Because now I no longer have an indeterminate form. So watch. As x goes to negative infinity, x to the fourth is going to approach positive infinity. 1 is a constant, so that's just going to approach 1. And 4 over x will approach 0. So the limit of something that's approaching infinity times 1 is just going to be infinity. So this means the limit in the positive and negative direction approaches infinity. So the function is not leveling off. We would have a horizontal asymptote if either of these limits was a constant, 0 or some other value. That would indicate that we have a horizontal asymptote. So we can see here, there's no horizontal asymptote. All right. What about vertical asymptotes? Well, those will only apply for rational functions. So in this case, we have a polynomial, right? F of x, which is x to the fourth plus 4x cubed, is not a rational function. The domain is all real numbers, so we have no vertical asymptote. But if you have a rational function, in order to find its vertical asymptote, what you need to do is first identify what the most simplified form of the function is. So for example, if you have a function here, I'm first going to look at g of x actually, which is 4x over x minus a, 4x times x minus a over x minus a. See how this is not in simplest form? Well, I would not have a vertical asymptote in this graph because the factor of x minus a can be canceled out. So you would only have a vertical asymptote if you have a factor that would make the denominator 0 and the function was already in simplest form. Okay, so if f of x was just 4x over x minus a, then the zeros of the denominator, or x equals a, would be where we would have a vertical asymptote. But if you have a factor that cancels and there's no longer some value that would make the denominator 0, then you just have a hole in the graph, which you would represent with an open circle, an actual hole. And the other case is an oblique or slant asymptote. This happens in rational functions where the numerator's degree is 1 more than the denominator's degree, and it has to be exactly by 1. Now, after long division, the quotient is the equation of the oblique asymptote. And just in case you need a reminder, f of x equals 2x cubed plus x squared plus x plus 3 over x squared plus 2x. This function would have an oblique asymptote because notice the degree in the numerator is 3 and the degree in the denominator is 2, which the degree of the numerator is exactly 1 degree higher than the degree of the denominator, so we have a slant or oblique asymptote. So let's just work through the long division. If you need a full review of long division, then there's a video, I'll link it below, for you to watch that will go through the process step by step. So here we're going to take the divisor, which is the denominator, x squared plus 2x, list it outside, and then the dividend is the stuff in the numerator, 2x cubed plus x squared plus x plus 3. And remember, when you're long dividing, you just pay attention to the leading term. So you think, okay, what do I need to multiply x squared by to make it 2x cubed? Well, that's a 2x. So then you're going to multiply that value by the divisor. So we'll have 2x cubed plus 4x squared. And then we subtract in the next step. This leading term to the left should always cancel out. And then now I have a negative x squared. Then I bring down the next term, bring down the x, and continue the process. So I'm just going to focus on x squared. What do I need to multiply it by to make it a negative 3x squared? Well, that would be a negative 3. And then multiplying again by the divisor, I have negative 3x squared minus 6x. I subtract this. These should cancel. And I'm left with 7x plus 3. Now this is my remainder. The remainder is not included in the equation of the oblique asymptote. So the equation of the oblique asymptote is y equals 2x minus 3. The reason why the remainder is not included is because the remainder technically would be 7x plus 3 over x squared plus 2x, right? If we had our oblique asymptote written in the following form. And as we know, when we take infinite limits, as x approaches infinity, since the degree of the denominator is higher than the degree of the numerator, the remainder would approach 0. And this is always true. And our asymptotes give us information about the end behavior of a graph for large values of x in the positive and negative direction. So the remainder is always irrelevant. Okay, so that was just a quick review of long division, but if you need more, then you can watch the video that's going to be linked above. Next is finding intervals of increase and decrease. So now we're going to put to use all of the calculus that we worked so hard on the past few sections. So remember, our function is f of x equals x to the fourth plus 4x cubed. So to find intervals of increase and decrease, remember I need to look at f prime of x. So I'm going to go ahead and take the derivative, and that's going to be 4x cubed plus 12x squared. And now I want to find the critical values. And remember, we obtain critical values from two places, where either f prime of x equals 0 or where f prime of x does not exist. Now, if f prime of x equals 0, that would mean my derivative, 4x cubed plus 12x squared equals 0. And to solve from here, I could just take out the greatest common factor, 4x squared, and I'm left with x plus 3 as my other factor. And then using the zero product property, I get that x is equal to 0 or negative 3, and these are two of my critical values. Now, what about where f prime of x does not exist? Well, f prime is another polynomial. It exists everywhere, so there's none from this second scenario. All right, well, now that we have our critical values, we need to test our intervals to see where the function is increasing and decreasing on a number line. So remember, label your number line f prime of x if you're testing for increase and decrease, and then put your critical numbers on there. So I'm going to put negative 3 and 0. And remember, when you're testing them in f prime of x, whatever you labeled your number line, okay? So let's test a value within the interval from negative infinity to negative 3. And I recommend testing in the factored form because it's going to make it the easiest possible for you to evaluate. So say you pick like negative 4 to plug in. Well, if I plug in negative 4 into this first part of f prime, it's going to be positive, right? Because it's squared. And then negative 4 plus 3 is going to be negative. So a positive times a negative, that means my derivative is negative here, which tells me that f of x, my function, is decreasing. So draw yourself a little arrow going downward, that way you remember. Okay, what about between negative 3 and 0? What's a good representative there? Maybe negative 1, negative 2, whatever you like. So plugging in for 4x squared, that's going to be positive, doesn't matter. And then negative 1 plus 3, negative 2 plus 3, that's going to be positive. So a positive times a positive means the derivative is positive, which means our function is increasing on this interval. And then lastly, larger than 0, you could pick 1, 5, 42, doesn't matter. Both quantities are positive, so the derivative is positive here. All right, so what does this tell us? Well, my function is decreasing on the interval from negative infinity to negative 3, and it's increasing on the interval from negative 3 to 0, union 0 to 3, or 0 to infinity, excuse me. Now you cannot just write negative 3 to positive infinity. You must exclude 0 from the interval of increase because remember, the derivative is equal to 0 at x equals 0, which means that the function is flat or constant for that moment, for that instantaneous moment. So you must skip over it when listing intervals of increase or decrease. All right, next step, part F, we have to identify any local mins or maxes. Well, do we have any of those? Look at your graph, it'll help. So the number line up above demonstrates clearly we have a local min when x equals negative 3, and I want to evaluate it in our function. So f of negative 3, this is how you should always list out your answer. Remember, f of x was x to the 4th, so we have negative 3 to the 4th plus 4 times x cubed times negative 3 cubed. So that's going to be a positive 81 plus 4 times negative 27. This gives us negative 27. All right. What about any local maxes? No, there aren't any in this case. Notice the other two intervals, the function is increasing. It never switched back to decreasing, so there's no local max. You still need to state this to indicate that you thought about it, okay? Very good. Let's move on to the next step, concavity and inflection points. So where do we get information about concavity from? That's right, the second derivative. So if you'll recall, f prime of x was 4x cubed plus 12x squared. So the second derivative, f double prime of x, is equal to 12x squared plus 24x. All right? Now, I want to identify possible inflection points. Those come from two places again, where f double prime of x equals 0 or where f double prime of x does not exist. Well, let's see. If f double prime equals 0, this would mean 12x squared plus 24x equals 0. Again, I'll solve by taking out the GCF. So if I factor out a 12x, I'm left with x plus 2 equals 0. So solving for x, I'm going to get x is equal to 0 or negative 2. All right, what about where f double prime does not exist? Well, again, f double prime is a polynomial, so there's no places where it doesn't exist. So there's no new x values here. Again, I'm going to test my intervals of concavity. So we're going to make a number line. This time, label your number line f double prime of x, right? Since that's what we're going to be plugging these values into in order to check where the graph is concave up and concave down. All right, again, I recommend plugging it into the factored form of f double prime. It's just going to make testing for the sign that much easier, okay? So say you're picking something from negative infinity to negative 2, like negative 3. Well, if I plug that in for 12x, that's going to be negative. And then negative 3 plus 2, that's also negative. So a negative times a negative is positive, which means our graph is concave up on this interval. What about from negative 2 to 0? Say you plug in something like negative 1. Well, 12 times negative 1, that's negative. But negative 1 plus 2 is positive, and a negative times a positive is negative. So the graph is concave down there. And then last interval from 0 to positive infinity, I can see clearly 12x and x plus 2 are both going to be positive, so the graph is concave up. All right, so now I'm ready to list my intervals of concavity. The function or the graph is concave up from negative infinity to negative 2 union 0 to infinity. And it's concave down from negative 2 to 0, just in the middle there. And now for the last step, I want to identify any inflection points. Do we see any points where the graph changed in concavity? Well, yes, both negative 2 and 0, we noticed there was a change in concavity at these x values. So remember, plug these into the original function. So f of negative 2, that's going to be negative 2 to the 4th plus 4 times negative 2 cubed, which gives us negative 16. And then f of 0, that's our favorite one to plug in. It's just 0. All right, so we've done all the groundwork. Now we get to do the fun part and put everything together and sketch the curve. So what I like to do when I start is list out all of the information that we obtained in the previous steps. That way I know what important points or features I need to include in the graph. Okay, so we have here our intercepts at 0, 0 and negative 4, 0. Okay, so let's plot those. 0, 0 and negative 4, 0. Actually, let's list everything so I know how to scale. Then, did we have any local mins or maxes? Yes, I had a local min. It was f of negative 3, which is negative 27. And then did we have any inflection points? Yes. F of negative 2, which was negative 16, and f of 0, which was 0. So since it looks like I need to scale all the way down to negative 27, I'm going to scale my y-axis by 3s. All right, so this is going to be negative 3, negative 6, negative 9, 12, 15, negative 18, 21, 24, negative 27. Okay, that way it'll fit. And then the x-axis, it doesn't look like I have any really extreme x values, so I'm just going to scale by 1s. 1, 2, 3. This will be negative 4, so I'll call this negative 5. Here's my x-axis, y-axis. Always be sure to label that. And then this is positive 1, 2, 3, 4, 5. All right, so now we're ready to start graphing. So we have 0, 0 is an intercept, as well as negative 4, 0. Okay, I have a local min. F of negative 3 is negative 27. So 1, 2, 3, negative 27. It's going to be right here. I'm going to remind myself that's my min. Okay, local min. And then f of negative 2 is negative 16. That would be right around here. And f of 0 is 0. I already have that. So this is an inflection point. And this is also an inflection point. Okay, well, if you need to reference some of the information before, it might be helpful. Because, for example, the graph is concave up from negative infinity to negative 2. So up until this inflection point right here, the graph is concave up. Well, concave up looks something like this, right? So that means the graph is going to have that shape resembling a parabola that opens upward. And I'm just going to make sure that as I pass through here, I demonstrate that this is the min at negative 3. And then I'm going to start increasing up until this inflection point. I'm actually going to keep increasing, right? Because that's the only local min. And then I want to show that there's some sort of change in inflection right there. So now the graph has to start looking concave down past negative 2. If this is a little tricky, remember what x cubed does. X cubed switches from concave down to concave up. So you can do something similar here. And then the rest of the way, the graph is going to be increasing, right? We only had that one local min. So the graph should just keep going up, 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 up. But it's concave down until it hits 0. Then remember at 0, 0, we had another inflection point. So now it's going to switch back to concave up. and then put arrows on your graph to indicate. This matches the end behavior that we found in the beginning when we took the limit as x approaches positive and negative infinity. All right, so there's our completed graph. If you don't feel confident as you're plotting everything and sketching the graph, you're more than welcome to make a table of values. But typically, if you use all the information that you found in steps A through G, you'll be able to draw a very accurate and precise graph. Just make sure everything is scaled and labeled appropriately. All right, let's look at another example, this time working with a rational function, y equals 1 over x squared minus 16. And the first thing I want to do is just factor this denominator into x minus 4 and x plus 4 before I proceed. So the first step, remember, is to identify the domain. And I can see that we have two restrictions. So you can either write your domain in set builder notation, x, such that x does not equal plus or minus 4. Or you could write it in interval notation. So excluding 4 and negative 4, we would write from negative infinity to negative 4, union, negative 4 to 4, union the interval from 4 to infinity. So keep those two restrictions in mind. All right, next step is to find intercepts. So x-intercepts come from setting y equal to 0 or the function equal to 0. Well, clearly the numerator is never going to equal 0, so I have none. As far as the y-intercept, I'm going to substitute 0 in for x, so that's going to be 1 over 0 squared minus 16, which is negative 1/16. So always list your intercepts as ordered pairs. I have one intercept, the y-intercept, 0, negative 1/16. All right, very nice. Step C, I want to test for any symmetry. So I do that by determining if the function is even, odd, or neither. So the test is I evaluate f of negative x. That's going to be 1 over negative x squared minus 16. And so this is just going to give me back 1 over x squared minus 16, which is the same as the original f of x that we started with. And by definition, this means I have an even function. So my graph is symmetric about the y-axis. So we're going to keep this in mind, especially when we're graphing, because it's going to be very helpful. All right, now what about our asymptotes? Well, to begin with, let's look at our end behavior as x approaches positive or negative infinity. So the limit as x approaches positive infinity of f of x of 1 over x squared minus 16. Well, the denominator is going to be getting larger and larger, and the numerator is a constant, so this approaches 0. And the same would be the case if we went to negative infinity, right? 1 over x squared minus 16, constant in the top, bottom's blowing up, so this is 0. So notice in this case, we got a constant. This means my horizontal asymptote is at y equals 0. You must write y equals. That way it's clear that it's a horizontal asymptote. If you have a horizontal asymptote, then you don't have a slant asymptote. You will never have both. It's either one or the other. So that means there's no slant asymptote. Another way to check is you have a horizontal asymptote for a rational function if the degree of the numerator is either equal to the degree of the denominator or lower than the degree of the denominator. In any other case, you would not have a horizontal asymptote. And then the other thing we need to check for are any vertical asymptotes. And that happens when the denominator equals 0 after the function is in simplest form. And we have two of them at x equals 4 and negative 4. Be sure you write x equals, and this is why it's such a big deal that you don't write your intercepts as just x equals whatever, and you write your intercepts as ordered pairs to distinguish them from the equations of asymptotes. All right, moving on, let's find intervals of increase and decrease. So figure out where the function is increasing and decreasing. So remember, f of x was 1 over x squared minus 16. So I need to first compute f prime of x. Now be kind to yourself. There's no need to do the quotient rule. The numerator is just a constant. So that means I can rewrite f of x as x squared minus 16 to the negative first. And now to find the derivative, I'm just going to apply the chain rule. So f prime of x is going to be negative 1. Leave that quantity alone. Subtract 1 from the exponent. Now I'm going to rewrite x squared minus 16. Don't touch it. And then multiply it by its derivative via the chain rule, 2x. Now I'm going to clean things up. So I get negative 2x over x squared minus 16 squared. So this is f prime of x. Beautiful. Now I need to find my critical values. Remember, they come from two places. Either where f prime of x equals 0, or where f prime of x does not exist. So f prime of x equals 0, that would mean the numerator of my derivative would equal 0. So this would mean negative 2x equals 0, which would give me x equals 0. All right, so that's a critical value right there. Other place I get critical values are where f prime doesn't exist. So that would mean the denominator, x squared minus 16 squared, equals 0. Well, that would mean x equals plus or minus 4. But remember, these are not elements of the domain. So they are not critical values. However, I will still list them on my number line when I'm testing for where the function is increasing or decreasing. But they cannot be local mins or maxes or critical values. All right, so let's go ahead, make our number line. I'm going to include everything from above, plus or minus 4 as well as 0. So negative 4, 0, and 4. Now look, we're going to test the intervals. Don't forget to label it, f prime of x. I'm going to test the intervals in this boxed version of the derivative that I have. And look at something that's really nice. The denominator is a quantity squared, so the denominator is always going to be positive. That means when I'm testing values from the intervals, I'm only going to look at the numerator and just substitute them in for x. Okay, so for example, if I'm testing a value on the interval from negative infinity to negative 4, like negative 5, I'm just going to check if I plug in negative 5 here, negative 2 times negative 5, that's positive, and I know the denominator is always positive, which means f prime is positive here. So my function is increasing on that interval. Okay, what about from negative 4 to 0? Like negative 1. Again, the numerator is going to be positive, denominator is always positive, so the function is increasing here. All right, from 0 to 4, say you plug in 1, negative 2 times 1, that's negative, so the function is decreasing. And then same thing on the other side of 4, if you plug in 5, it's negative, so the function's decreasing. All right, so let's list our intervals. The function is increasing from negative infinity. You cannot include negative 4. Remember, it's not in the domain, so the function doesn't even exist there. You can't say it's increasing there. Union, negative 4 to 0, and then the function is decreasing from 0 to 4, union 4 to infinity. All right, be very, very careful anytime you have restrictions in the domain. All right, part F, do we have any local mins or maxes? Well, it looks like f of 0, which is negative 1/16, we found that earlier, is a local max. Doesn't it look like a max right here? But there is no local min, and make sure you state that. All right, last portion that we need to analyze is the concavity and any inflection points. So concavity and inflection points. Well, where do we get information about concavity from? The second derivative. So I need to compute f double prime of x. So remember, f prime of x was equal to negative 2x over x squared minus 16 squared. So yes, this time I must use the quotient rule since I have variables in the numerator as well as the denominator. So f prime of x is going to be low d high, so denominator, times derivative of the numerator, negative 2, minus high d low, so negative 2x, times derivative of the denominator, which is going to be 2, times x squared minus 16 to the first, times a 2x by the chain rule, over the denominator squared, so x squared minus 16 to the fourth this time. All right, so let's clean up a little bit and factor out the GCF. So what can I take out from all the terms? Well, I can take out a 2, and I can also take out an x squared minus 16. All right, and then let's see what's going to be left over. So if I take out a 2 and I take out one of these x squared minus 16s, I'm going to be left with a negative x squared minus 16. And then in the next term, let's see here, these two negatives are going to make a positive. And then I'm taking out a 2 and an x squared minus 16. So all that I'm left with is a 4x squared positive. And then this is over x squared minus 16 to the fourth. So now I can see this x squared minus 16 is going to cancel. This is only to the third. And then I'm going to have here, this is a negative x squared plus 16 plus 4x squared. So I have 2 times 3x squared plus 16 over x squared minus 16 cubed. Okay, and you want to leave it factored like that in the numerator because then it's easier to identify the zeros, right? Let's box it. That way we know we have a finished product. And then let's see, possible inflection points. So I want to look at where f double prime of x equals 0 and where f double prime of x does not exist. So if f double prime of x equals 0, that means the numerator equals 0, which would mean 3x squared plus 16 would equal 0, which would mean 3x squared would equal negative 16, but that's not possible, right? We wouldn't get a real solution to that. So there's none. What about where f prime of x doesn't exist? Again, that would mean the denominator equals 0, which would mean x squared minus 16 equals 0, which would mean x equals plus or minus 4. But remember, these are not elements of the domain. So these are not going to be inflection points. But remember, when I'm testing for intervals of concavity, I do still need to break up the intervals here since the function may change its behavior on either side. They won't be inflection points, but I still need to list them when I'm testing for my concavity. Okay, so the only values here are going to be negative 4 and positive 4. Label your number line, f double prime of x, and let's start checking. So look here at f double prime. I have it boxed up above. And notice that the numerator is never negative. So I'm not even going to look at the numerator. When I'm testing values, I'm just going to substitute them into the denominator and see what's going on. So say I plug in something like negative 5. Well, negative 5 squared is positive 25 minus 16. That's going to be positive. So the second derivative is positive, which means the graph is concave up. Say you want to test the interval from negative 4 to 4. Nice number to pick is 0. Well, looking in the denominator only, 0 minus 16, that's negative. Numerator is always positive, so second derivative is negative. Graph is concave down. And then something larger than 4, if I plug it in for x here, 5, 6, whatever, it's going to be larger than 16. So the denominator is positive. The whole second derivative is positive. So the graph is concave up. All right, now I'm ready to answer this last part here. The graph is concave up from negative infinity to negative 4, union 4 to infinity, and it's concave down from negative 4 to 4. Do I have any inflection points? No, because remember, negative 4 and 4 are not in the domain. So state that there are no inflection points. All right, very good. Let's box this part here. And then now the fun part comes, we get to put together our graph. All right, well, let's include information that we had all along the way. Our intercepts, our intervals of increase and decrease, and all that good stuff. Okay, x-axis, y-axis. So remember, I had a y-intercept at 0, negative 1/16. I had vertical asymptotes at x equals plus or minus 4. I had a horizontal asymptote at y equals 0. And then I'll include all the information about concavity in just a minute. So positive and negative 4 are where my vertical asymptotes are. Let me not spread it out so much. 1, 2, 3, 4. Negative 1, 2, 3, 4. So these are where our vertical asymptotes are. You want to indicate that with dashed lines. 1 there. 1 at negative 4. I have a horizontal asymptote at y equals 0. So right on top of the x-axis. If you want to remind yourself, you can just draw a little bit of dashed lines extended beyond the axis to remind you. So here's y equals 0. Here's x equals 4. And x equals negative 4. And the only other point I have is my y-intercept at 0, negative 1/16. So that's a very small value. Just label it clearly. This is negative 1/16, 0, negative 1/16. And remember, I have y-axis symmetry, which is going to be really helpful. Which means if I fold my graph along the y-axis, I'm going to have a mirror image. So let's recall, we can actually use the concavity to help us. The graph is concave down on the interval from negative 4 to 4. So that means on this middle portion of the graph, it's concave down. So it's looking like a downward facing parabola. This value here is our max. And remember, there's no x-intercept. So this graph will never cross the x-axis. So what's the only way for it to be concave down and have a max at negative 1/16 like that? Well, it's going to look like a parabola, except it's trapped between the two asymptotes there. And make sure you draw it as symmetric as possible. You must include the arrows on the other side. All right, now what about on the other side? Our graph is concave up on the remaining portion. So there's really 3 parts to the graph. It's concave up over here from negative infinity to negative 4, and it's also concave up here. So all I need to determine is if it's increasing or decreasing. Remember, something that's concave up has this sort of a shape. So let's go back and check what the graph was doing on those intervals, if it was increasing or decreasing. And I'll just remind you here, so we don't have to scroll all the way back, that the graph was increasing from negative infinity to negative 4, as well as from negative 4 to 0. And then it was decreasing from 0 to 4, union 4 to infinity. So how can you draw something that's increasing on this portion of the graph and have it be concave up? Well, and not cross the x-axis too. It's going to have to be above the x-axis, and it approaches, remember our end behavior, our horizontal asymptote is y equals 0, and we have a vertical asymptote here. Again, if you're not certain, you could test values and make a table. How do I know that it's not down here? Well, that would be concave down. Remember, the graph has to be concave up and increasing on that interval. So that option won't work. And then what about on the other side? Well, remember we have symmetry about the y-axis, so it has to be a mirror image, but also we can check that it makes sense. Remember, the graph is going to be concave up there, and it has to be decreasing, and that's the only shape that works. If I were to draw something on the other side, that wouldn't work, that's concave down. And remember, no x-intercepts, so don't cross that x-axis. All right, so these are just 2 examples, but as you can see, as you work on the homework assignments, there's going to be a lot of other interesting situations that come up. So just be patient, be meticulous, and make sure you reference your notes while working.